Hi guys, technology check. Can you see and hear me? Yes, thank you. Yes, yeah. So we have finished our main block of our course, the univariate modeling of stationary processes. It's not the only thing to do with univariate processes, but this is the very basic one. And what we will do this week, today and tomorrow, is not going to be in your project, but it is still a very important block, and you will also have another quiz next week. That would be the last quiz. And of course, parts of the questions on the exam will be related to this topic. So we are talking today about multivariate modeling, and the very basic multivariate model, or the very basic multivariate tool in econometrics, is multivariate linear regression, the one that you are very well familiar with from the cross-sectional econometrics from your econometrics 1 course or econometrics 2, whatever. And today we are considering a special case of it, the multivariate linear regression for stationary and ergodic time series. So it might be a little relief that we are doing with not univariateness anymore, so there's not going to be ARMA stuff. So we are not going to recall anything that we did last time, but we are going to use a lot of things that you studied in econometrics 1 we needed, because this is the basic case for random sampling, the one that you covered in that course, and we are going to extend it to the case of stationary and ergodic time series, and tomorrow we are going to consider how to apply that in practice. A few baseline empirical examples. Just take a minute to think. We are not going to use Looklab to share the answers, but still take a minute to think or to remember actually from the econometrics 1 course. Why would we need multivariateness? So why do we use many variables together? Yeah, this is a very easy question, but just throw a few answers. It shouldn't take even as much as 1 minute. So we used to work with only one time series. Now we're going to work with several time series at the same time. Yeah, they are still going to be stationary, or stationary transformations. So what are your ideas? What is multivariate models about? What are they about? What do we need them for? Come on, like half of you are not using them in your econometry, in your time, not time, what's that, in your term papers, курсовиках. As compared to the one variable models, univariate models. What is the advantage of multivariate models? Less biased estimates of what, first of all? So far, the only estimate that we discussed biasness on or unbiasedness, we discussed only the predictions as estimates of unknown future values. Because we did not discuss any estimates of parameters of the models, for example, right? Their properties. It was not relevant in the prediction context.
Потому что другие переменные могут влиять на нашу переменную, и если мы будем их использовать, мы получим более точный ответ.
Yes, thank you. We are economists after all. We wonder how things are related to each other and how they affect each other. In time series context, we can extend what we know from econometrics and check different effects of one things on other things. This is one of the most commonly applied reason for using many variables in one model, to see how they are related and also to test whether there is some connections or something like that. There are other reasons, but we will see. And in time series context, you get a lot more possibilities other than in cross-sectional econometrics because of the possibility to use the difference in time. We will see. First, we need to recall the basic stuff about multivariate linear regression that we know for random samples. So this is still the repetition from of what you saw in the Econometrics 1 course. If something is not familiar, then please stop me and ask. But overall, we are going to try to go over it very fast, or well, faster than usually. So you are very well familiar with this kind of notation. So maybe you used something else in your course. In this course, I'm going to use this notation that is very widespread in textbooks and other courses. So get used to it if it's not familiar still. But overall, there's very little change from what you saw in econometrics course. There's going to be some change, some extension already to the very basic case of random sample, but not much. So this is the very well familiar by observation form. Why by observation? Because this states the linear regression model for only one observation. This is not yet, technically speaking, this is not yet a regression model because there is something missing. The same way as there was before in our questions, in some questions about ARMA processes. Do you remember that? Consider a time series process, blah, blah, and is there something missing? Yeah, something is missing about the error term, of course. Until we state some assumptions, it's not a model, but later about this. Now just about the notation. Then by observation means that yes, so this one expression shows the regression expression for one observation, the I, which is the object index in case of cross-sectional regression or random sampling. This is the index of the object, or the index of the observation, number of the observation. Then y I is the so-called dependent variable, or the variable of our main interest, the one to which we check the relation of other variables with. Or technically speaking, sometimes or very often we call the left-hand side variable, just because as economists and people who are familiar with the indigeneity problem, we understand that there is not really such thing as dependent and independent things. They are all interdependent together usually. So, but this is the left-hand side, the one that is, according to our model, maybe is affected by other things. So we will see. And axes are, well, there are k of axes from 1 to k, and there's also one extra, which is the constant here, but we don't see it yet. Other so-called explanatory variables, or sometimes they are called technically right-hand side variables because they appear on the right-hand side of the regression. Or sometimes we just call them regressors or covariates, less commonly used term, but also or controls. That depends on the field and slang and so on. So, but right-hand side variables will work for us well. But we don't call them anymore independent variables because, well, that's not what they are. They are not independent of anything. They are very well dependent with everything. And betas are k plus 1. In this case, k are correspond to the axis, and there's extra one beta naught, beta 0 that corresponds to the constant term in the regression. They are the regression coefficients or just the parameters of the regression. Sometimes there are other parameters than betas, but this is the basic setup of linear regression, very baseline setup. So these are the parameters of the regression. And epsilons are the residual error term, or sometimes just error term, and when we estimate, then we call it just residual because well, in the sample dependent on the data. But the full name of this guy is residual error term. But we will all just call it just the error. There are short annotations for that, and then please don't be confused by it. We are going to use it a lot on the slides so that not to expand this full notation all the time, this summation. So in short, if you join all the axes, all including the one, so if there are k explanatory variables, k controls, k covariates, and so on, that those right-hand side variables, then the dimensionality of the vector, when you combine them to the vector, and that is going to be a row vector because they are written in a row like that. This is the convenient way to write it down. Then the dimensionality of this thing is 1 by k plus 1. So it's a row, then hence 1 by k plus 1, because there's also unity there. And then beta is a column vector. This is k plus 1 times 1, or k plus 1 time, by 1. And this is the vector product, which is the summation of the products of elements of the vector, and plus the error term. Or in short, in the so-called matrix form, when we join them not only horizontally, those vectors, but also vertically. So each observation is put on top of each other, and you receive a vector of dependent variables or left-hand side variables for all the observations. Then the matrix of the right-hand side variables, the same vector of the coefficients as the in by observation term. It's common for all the observations, and the vector of error term, right? So this is very well familiar for you. Maybe you used another form of writing it down with some transpositions and so on, but this is exactly the same technically. Maybe if you change dimensionality a little bit, there might be x transposed and the beta on the other side, depending whether beta is column or row, but essentially it's exactly the same. So once again, y is n times 1 vector, because n is the number of the observations. Then x is n times, because n is again the number of observations, and each row of that matrix is the values, collects the values of those right-hand side variables for that particular observations, and you stack them on top of each other, right? So n times k plus 1 rows, and each row looks like this. It's xi, this one here. But the numeration starts not from 1, but from 0 or from naught. And the first one is 1 here. So there might be a little bit confusion, because we still call the value of those x's here but like xi1, xi2, xi3, but we understand that in the x matrix, this is the second column, not the first column of the matrix, because there's also this one. So a little bit of torturing of matrix algebra, but yeah, it's okay. And beta is the column vector 1 plus k times 1 vector of the coefficients, starting with the constant term, the one that is going to be multiplied by those ones, right? And then the betas corresponding to x's. Yeah, this prime means transposition, transposed, so this is the column vector. And this is a little cheat sheet for you in case you forget how it looks like and why it looks like this. But since you already had your projects in econometrics, I'm sure this is very well known to you. So this is how it looks like. This is the your sample of observations of the dependent or left-hand side variable stuck on top of each other as a column vector, right? N times 1. Then the matrix of x's, where the first column is the unity, which corresponds to inclusion of the constant term beta 0. Here it is, the first. In each row, this one will be multiplied by beta 0, beta naught, and then hence in the by observation form there appears beta naught plus, and then summation of all the x's with all the other betas. So betas are the same for all the coefficients and so on. And then the vector of residual error term, just error term in every for every observation, the same dimensionality as each column of X matrix or the column of Y's. So I hope so far no questions, but if there are any, then please ask now to avoid the confusion later, because this is the notation that we are going to use. Okay, let's move on. Now, not about the notation, but the actual model things. So far, the way that we stated it, this is, I called it a model or regression model, but this actually not a model. This is yet not a model fully, so model in quotation marks. This is not a model unless we have some assumptions about it. So we already stated something. So beta is the constant term, constant coefficients. So they are determined, not constant, but determined coefficients. So they are just numbers, not random variables. Everything else must be something random, because this is data that we obtain somehow from random sampling probably, or some other things. It doesn't matter. And then also we don't know anything about the error term. And unless we state something, we cannot call this a regression model. So for this thing to be actually a linear regression model, well, it is already linear, but for it to be actually a regression model, we need to state some assumptions. And I know that you had a lot, like a huge set of assumptions in the baseline econometrics course, right? And then you can see that what would happen if this is violated, if this is violated, like the very, very, very basic case where you studied the properties of the estimates. We are going to consider like a narrowed set of assumptions. So there are very shortly written down, but they contain all the same or almost the same information, almost the same assumptions. The first assumption, we will call it RS. RS stands for random sampling because we are considering the random sampling case. A1, assumption 1, random sampling assumption 1. This is the assumption of random sampling. We say that, okay, the data that we use comes from IID observations or comes from IID data generating process. It means that this whole thing, when we observe it in a sample, is assumed to be from IID. It doesn't mean that and IID, you know what that means, identically and independently distributed. It doesn't mean that y's are independent from x's and the same distribution, no, but jointly the distribution of those things is the same for all the observations. So IID across i's, across observations. For each observation, the distribution, the joint distribution of this thing is the same. It is the same, the same, the same. This is the assumption of random sampling. They are independent and, well, identically at least jointly, but there might be some deviation from this assumption that is not going to be terminal for the model, but this is the basic version of it. Because sometimes they might be identical, independently distributed, but maybe not exactly identical. Or who knows? A little bit of difference might be there, might appear there, for example, in the way of heteroscedasticity of those things. And the second assumption is the so-called exogeneity of the error term. This is very important, and this is the crucial assumption. Without it, this is not a regression model. It is just some expression of random variables that are not like even well, give us any basis to work with it. So with this assumption, we can work with this as a regression. Also, in the time series context later, we're going to need some extension of it, but not exactly the same. So the exogeneity of error term basically says, technically this, the conditional expectation of epsilon given axis is 0. How would you call it in terms of what you studied in econometrics 1? What is the meaning of this assumption? Except for exogeneity. This is the essential meaning, but another technical interpretation of it. You saw it many times. I expect that you maybe called it some other thing. Yeah, first of all, this as a consequence of this, you will have zero mean errors. Yes, the expectation of the error term is 0 because the conditional expectation is a random variable that depends on axis. And when you take them twice, the expectation of conditional expectation, you will just get the unconditional expectation of y, of epsilon, sorry, and it must be 0. Yeah, that's true. That's a consequence of this expectation. But what else? More importantly, or maybe not less importantly, at least. So yeah, that's why I said it looks like a narrow set of assumptions, but really all the same information is there. So zero expectation of the error term is there. What else is there in this assumption of zero conditional expectation? No, centrality is just a technical trick that we use sometimes, and there's no centrality because I said that in the axis there is one. There's a constant term. If we centralized all the data, then we wouldn't have the constant term, right? We would not need it. We might use it, but nothing will really change. Okay, this assumption essentially gives you uncorrelatedness. This is what it is. One thing to read this expression is like the conditional expectation of epsilons of the error term given axis is 0. The other thing is that the error term is uncorrelated with axis, with all of them, with each of them. So the error term is exogenous. That's why we call it exogenous. Exogenous means that, yeah, uncorrelated with axis. Whatever the axes are, the error term still is centered around 0. This is what allows us to get unbiased estimates of betas by very, very simple procedures such as the ordinary least squares. If this is violated, then yeah, we need something else. There's endogeneity, instrumental variables, blah, blah, a whole lot of pain in the neck and other body parts. So this is it. The zero mean errors here are here in this assumption. And second, the uncorrelatedness of errors and the right-hand side variables. In short, this is called the exogeneity of the error term, and it is expressed as the conditional expectation of epsilon given x is 0. And then, as I said, so given those assumptions, we can apply a very, very simple, well, not so simple, but very well familiar to us tool to estimate the betas, because betas are unknown, and one of the purposes of the analysis that involves multivariate linear regression supposes that we are going to estimate those coefficients, right? We want to estimate them and then maybe do something like test hypotheses and stuff like that, right? And the very, very well familiar thing to you and maybe a little bit painful, but get used to it. You are going to see it more. The ordinary least squares estimation. This is basically, this has a whole background of why it is applied. So it has very nice properties and guarantees some properties when the assumptions are fulfilled, when the assumptions hold. If not, then maybe something happens and we need some corrections and so on. But this is the basic setup. And when the assumptions hold, this what guarantees us very good estimates of the betas coefficients. We take some value of the betas, not the betas exactly because we don't know them, but suppose there's something like the vector of coefficients b, the same dimensionality of betas. So basically just plug in there some numbers. Call the difference between the right-hand side variable and the product of the left-hand side variables of the coefficients, the residual, square it up. So kind of like applying quadratic loss function to the difference between the actual values and what the right-hand side variables predict when we have coefficients b instead of the true beta that we don't know, right? So that's why residual we called, or this is the analog of the prediction error. It's not prediction error, it's fitting error. That's why the residual. Square it up, sum them up, those squares across all the observations, and minimize this summation with beta, or with b. This is going to be called, yeah, the result of this minimization is called the ordinary least squares estimate of beta, beta hat OLS. And this is very well familiar to you expression, right? There must be also another assumption that we missed here, right? So for this thing to work. Do you remember it in the light of application of the OLS? What assumption is missing there?
Нормальность ошибок.
It's not really missing. We don't miss it. We are glad when it's missing because no one likes normality of the errors. Actually, yeah, it's missing on purpose, and it does not affect in any way the ability to apply OLS, but something else does. something about this first part. It's really not a nice thing sometimes. So what is it essentially, this
Full
thing?
rank.
Hmm?
Full rank of
Yes,
metrics.
so basically the assumption of no collinearity of axes. This is what allows us to apply. So it's not here, but we assume that, okay, so there's no multicollinearity, right? So axes are axes in this thing. Yeah, so the matrix of axes is such that when you take the cross product of it, it gives you full rank matrix in terms of data, right? So this thing is invertible, which means that it's strictly positive definite. The determinant of it is positive and very far from zero, probably. Then we can actually apply it, this formula. Otherwise, we won't be able to apply it. We will get something like the matrix analog of division by zero here, right? When this matrix is not invertible, and that means that axes are linearly correlated to each other, linearly dependent to each other. So that assumption is missing there, but we somehow assume, okay, so it is there, let it be. It still might happen that the assumption is violated. The model is still a legit regression model. We can work with it. Just OLS will not be able to apply it. Yeah, okay, not such a big loss, but in our case, we assume that we can apply it. That means that that assumption is also there. If you don't remember how to derive it, it's a useful skill. So please spend some time to do that. And the important question is then when we estimated betas, so basically what we have beta, the true betas are some unknown things, unknown numbers, and these are the estimates which depend on the data, because, right, so we just saw x's and y's are the data matrices. This is all the data that we have related to that model. So how they relate to actual betas, and why in particular we love the ordinary least squares estimates. So there are several things. Normally we would spend some time. These slides I did not modify them from that time when the course was taking place simultaneously with Econometrics 1, so that there was a usual exercise, but I believe that now you are supposed to know that. So what we do, we take the difference between the actual estimates and the true estimates, the actual betas and the estimated coefficients. Sorry, I said something crazy. And then we try to describe it somehow. So first of all, we take the expectation value of this difference and find out that it is zero. Okay, the estimate is unbiased. Well, it might be still zero, but might still not be zero when some assumptions are violated. But because of some assumptions, we get zero there. So do you remember which assumption allows us to get zero expectation of this difference? This should be very easy now, because there's only one assumption about
The second one.
Yeah, the second one about the uncorrelatedness and zero expectation of the error term given the axis. Yeah, it gives you unbiasedness. This is the result of this expectation of this difference. This difference in expectation is zero. It means that the beta hat OLS are unbiased estimates of the true betas. Then what happens when the sample is huge? This is not such a nice maybe trick, not such easy exercise as taking the expectation, but what would happen? Do you remember? And thanks to what assumptions it happens? Yeah. If you don't remember what exactly happened, then you can try to recall
Нет,
the properties of the estimates.
Там, когда стремиться к бесконечности, там какая-то муть начиналась уже, поэтому сложно вспомнить. Но к нулю это тоже должно стремиться.
Yeah, it is not such a disaster there, but this difference diminishes. It converges to 0 when you drive the the sample size to 0. Why? Because like, let's try to imagine really short. This thing, the matrix product, right? When sample size increases, this thing, it happens with something happens with it, because what matrix product is essentially, it's something like a huge summation of some things, right? So it's product plus another product plus another product plus another product, so big summation. This is also another big summation, and then there's like a division of them. And when sample size increases, so something happens. It increases, increases, increases. Some limiting theorems start to work. Well, I get unstable internet connection notification. Can you hear me? Yeah, there was something about the covariation matrix. You're saying it like you had this course like 10 years ago or something.
Не-не-не, там эта тема просто очень мутно как-то. Ну вот типа вот эта матрица, она там на бесконечности, если поделить ее на n, то она куда-то к чему-то, почему-то сойдется. Вот это
Yeah,
вот без
that's
объяснения
the
как-то.
question. Why? Because this is very important.
А, why
It's
мы не
crucial,
знаем.
important why. You know, if you didn't get it on the econometrics course, believe me, you also knew it before. Why some average, something like average converges to something that is not average but some constant when the sample size of that average grows?
Закон больших чисел.
Yes, there's nothing else basically. Well, nothing else that you yet know.
Ну,
Yeah, due to law of large numbers or other things like that, yes.
И средний, откуда там средний? Ладно, не важно.
Yeah. Unfortunately, it is important. Yeah, okay. Let's try to do it. No. My virtual
Давайте
host,
оставим как упражнение для дома. Вот.
it is impossible. No. Yeah, unfortunately, this thing doesn't work. I cannot write in Zoom. Damn it. Let me try once again. Slow down a little bit, and then we'll get back there. Do you see what I see, the black screen?
Да, у нас тоже черный экран.
Yeah, so this is now definitely a Zoom problem, because it happened already before at some point. Okay, so I cannot share my writing, unfortunately. That's the problem. I will try to fix it by tomorrow somehow. Yeah, maybe. No, I could try to join from my tablet, my display. So yeah, you are exactly right. I mean, Roman, you are exactly right. So when you multiply both those things by n, by the sample size, inside the brackets and outside, it doesn't change anything, because here's you have inversion, right? So it's like multiplying the denominator and numerator of a fraction by the same number. And as n gets to infinity, this thing converges to something, this thing converges to something, and this works because you have IIDness of observations, this assumption, and all the sample averages across those observations converge to something due to law of large numbers. Yes, exactly, because of IIDness. If you don't have IIDness there, if those observations were dependent somehow, then yeah, we are in trouble. Basically, we don't get we don't get consistency of the estimates. And what is more important, based on that consistency, we get the most important result about that estimate. When we a little bit like slow down that convergence of that difference, we don't just get it to 0 as n grows to infinity, but we slow it down. So multiply it by something that grows to infinity, but not fast enough, so that in the limit there is not 0, there is not infinity, but something in between. And something not constant, but something random, right? So you can imagine this. You saw it many times. Square root of n times something ugly as n grows to infinity converges to something random. And that would, so before that, that would be called applying the central limit theorem and get the asymptotic normality of the estimates. When there is assumption of the normality of the error term that I said it's missing on purpose, you get this without any convergence, without the necessity to apply central limit theorem, центральная предельная теорема, the CLT. When you don't have that assumption, you still get the asymptotic normality. So when the sample size is huge, the distribution of this difference multiplied by something is approximately normal. This is what we get. And how those assumptions are related here? Yeah, without the second assumption of uncorrelatedness, we don't get unbiasedness. We don't get this zero difference. We might get that, but usually not. But more importantly, without IIDness of the observations, we don't get those convergences, like that consistency of estimates, the convergence of the difference to 0. And we are not able to apply the central limit theorem, and we are not able to say anything about the distribution, well, unless we apply something else, of course, or we know something about the dependency. But in the same context, we cannot apply the central limit theorem, and the result about the normality of the distribution doesn't work. So basically, we cannot run tests about our estimates and about the true parameters and do the inference, like estimate the confidence intervals, test hypotheses, and so on. Even predictions won't make any sense. So this is why the assumptions are crucial. And now the important questions, of course, for us is going, what does it mean for us when we deal with time series? So this is what I was trying to explain, like waving hands. This difference, if you cross out the square root of n, right? If you cross out the square root of n, where does it be? It will cross out this 1/2. It will be -1 just because n minus 1, so division by n, minus 1 division by n here. And they cancel out because of this inversion, right? So this is like the dividing and multiplying the numerator and denominator of a fraction by the same number n. This converges somewhere, this converges somewhere else according to central limit theorem. Then the product of those things also converge to some place because of some other theorems. Probably you know that, you know those theorems, maybe you don't. Now it's not important, but intuitively it's very clear, should be very clear. If this thing converges somewhere, there's a limit. This thing converges somewhere as n goes to infinity, there's a limit. Then the inversion of that of the thing also converges to the inversion of that limit, because that limit is not 0. And we know that it is not 0, that limit, because of that additional assumption that we skipped about full rank of this thing, of X prime X matrix. Yeah, and because we have those assumptions of IIDness, so this is the question is about what assumptions and what theorems we use. Because we have the assumptions of IIDness, we can apply the law of large numbers, and we can apply the central limit theorem in the second part, and then also some other theorems. I'm not sure whether you use them sometimes or not. If you had never heard about them, then it's okay. Now, if you did hear about them, then it's great. So we also need the so-called Mann-Wald theorem and maybe Slutsky theorem. теорема Манавальда и Слуцкого, for transforming the limits of the convergences, because we are not just taking some limit, but we also take the inversion of that limit, right? And there's also a theorem that says, okay, when something converges somewhere and you inverse it, the limit of the inverse thing is also the inversion of that limit, because it's something very intuitive but not obvious. If you didn't use that, that's okay. So just let's call it intuition, even though it's a limit. It's a theorem. So as a result of the combination of all those theorems and those assumptions together, but most importantly, law of large numbers, central limit theorem, and IIDness of observations, we get this. So the difference slowed down by the square root of n converges to normal something with zero mean. Why zero mean? Yeah, because of consistency, because this difference converges to zero when n is infinite. And with some unknown, because it depends on the true beta, but constant and a very legit covariance matrix. So this is this thing which we estimate from the data and then use to get, for example, our standard errors from, right? So why this is important? Yeah, well, this is of crucial importance in the random sampling context, because this is all that we use to do all the operations with estimated models. Test hypotheses, see whether we can say something about the importance of some right-hand side variables in the model of the left-hand side variable, and so on, right? So this is what we do with the models. And another question, so what do we do with that V beta, which is the variance covariance matrix of those estimates, of the difference of the estimates, right? We are not going to find it because, again, so you did it many times for the case of, or maybe you did not do it, but you saw it for the case of the random sampling, right? And then it changes if some assumptions are violated. For example, this is very easy to estimate, to find and estimate when there's the case of homoscedasticity, because some things just cancel each other out. If you remember it now, then great. If not, then it might be a sign that you need to revise it yourself. And then when, for example, you get heteroscedasticity, there it boom and it blows up. There's some huge stuff. Then that same stuff inversed. Then in the middle, some ugly matrices multiplied, inversed, multiplied again, and so on. That's like, okay. And this is our this is the matrix from which we get the standard errors. Okay, so as students, you usually do this. Okay, what we need to remember is that in Stata we use robust. Done. Well, that's a legit approach, but unfortunately now you will see even more ugly stuff, and it is generally it is a good idea to try to understand where it comes from and why it is important. So the importance of this thing and understanding of how it looks like for each particular case of your situation, of your model, of your assumptions, guarantees that you are not going to what's the right word here that it can be said in the audience, so that you are not going to do any silly mistakes in doing inference about your model. Because if you misplaced stuff estimating this guy, all your inference, all your judgment about the coefficients, their significance, the hypothesis that you check, well, it might just go to hell. So that's why, and yeah, and of course, how it looks like really depends on your assumptions and whether they are legit or not in the case of your data. And of course, IIDness of epsilons is very crucial because, well, it happens sometimes, but not often, as you know. Also, exogeneity of epsilons is also a very strong assumption, and often in economic context it fails. So that's why we have all those instrumental variables, tricks, and so on to deal with it, right? Okay, but the most important question of this lecture for us, so this is that what we saw before, what or so far up to this slide. So this is something that based on random sampling, right? And basically you are supposed to have seen already this thing, all of this. So this is what you do when you work with cross sections, classic cross sections without any indigeneity and stuff. And then the question is, can we apply the results to the time series case? So what do you think? And if yes, then in which case? So can we imagine the case where this thing can be applicable right away without any damage to the time series context? And if not, then why?
Yes, if the properties are hold.
Yeah, which ones again? And
Everyone.
is it realistic?
Maybe.
Yes. So you're right. So if
No.
we can make sure that those not properties but the assumptions hold, right? And one of the crucial assumptions, as we said, is the IID-ness, right? IID-ness of stuff, of epsilons, and IID-ness of x's and y's too, because these things also must be IID across observations for this whole summation to converge somewhere. And these products must be, that means that x's must be IID across observations. And for time series, we know that, yeah, this is in the nature of time series, that those things are not IID. They might be stationary, they might fluctuate around some constant, constant level on average. So they can be weakly stationary in mean, maybe even in variance, right? They might be even strictly stationary, even though we cannot check that usually. But it is in the nature that they are not IID, they are not independently and identically distributed. If the distribution changes, maybe even the average level change, the mean change, right? So we saw that in non-stationarity. There might be other problems like seasonality and stuff. And those results, they fail. No law of large numbers for not an IID case. Well, there is a version of it, but it is not exactly the law of large numbers. And the central limit theorem also doesn't work because we don't have that consistency there inside. And this thing, what's it gonna be then? Because it will look nice because of this summation. And because of the uncorrelatedness, yes, is going to be a diagonal matrix, because across observations, those things are not correlated. Remember, they are identically and independently distributed. It means that their product are also such. And inside this matrix, probably there will be not much things from outside the diagonal. They will only be related to these things. But this is technical stuff. And
So,
what is going
so
to be
you
there?
imply that
What?
our dependent independent variables are legs of the dependent variable.
That depends. It might be anything. It might
I
be
thought you would
left
use
values
other
and so on.
variables from another time series.
Yes, other variables, left variables, other left variables, and so on, of course. It doesn't matter.
So,
They are time series, and when they are time series, right? So imagine here. So it doesn't matter what is here. So y might be some variable. One of the axes might be y shifted, right? So it might be y taken with a lag. So y1 will depend on y minus 1, y minus 2, and so on. Well, it will not, but y2 will depend on y1 and so on. But then there also might be some kind of x, and it might be also shifted. So the another column of that matrix would be shifted back, taken with a lag in time, that x. And tomorrow in the empirical example, we will see. So the left-hand side variable would be GDP growth, and the right-hand side variables would be a lot of stuff related to housing starts in the economy. So basically how many new buildings are built in the economy. And we will try to check if there's any effect of constructing more buildings on the GDP growth. It's a legit empirical question. People ask it, pose it, and try to answer. But yeah, of course, the variables are going to be time series and
So if we pull from every time series no more than one leg or one variable, then the property of IDs of x's will be hold.
no, well, they are still not IID.
Ah,
Okay, let's go back again. They must be IID across observations, right? So if you have y1 here, y0 here, right? So you see that already, and you suppose that there is some not IIDness already in the y's, because this is a time series. Imagine that this is a GDP growth. It depends. If you use, depends on its previous values, the future values depend on the previous values and so on. Because there's some persistence in the economy. What we have today depends on what we had yesterday and so on, or this year depends on what we had last year. This is how economy works. Things are interdependent across time. Not only economy works, but this is how many things work. Not only social, society.
How to say it? No, я по-русски буду уже, что-то слишком сложно. Но идея в том, что как бы у переменных-то все равно одна и та же, один и тот же DGP, Data Generating Process. То есть как бы получается, что в моем случае они все независимы друг относительно друга, но если по наблюдению смотреть, то у них один процесс, как бы, из которого они выходят.
Yes, the process
Поэтому
is the same process, but they are essentially they are dependent. They are not IID. Process is the same, but you do not draw them independently. Independence and IIDness means that the order doesn't matter. It doesn't matter in which order they come. They represent different realization of the same like ideal object in that probability space, if you look at this. So even cross sections are not independent, really. But then you can assume, okay, so the dependence between cross-sectional observation is the dependence is minor, so we can like disregard it. But they are still dependent because of the sampling process, because of the network effects and so on. And in time series, no, you cannot disregard that dependence because they come ordered in time. There are some characteristics of that or of those periods in time that are like that they are not just missing from the model. It's not something missing knowledge. It's something that lies beyond the process that you describe, and it affects it. Economy grows. Economies grow in the world. It means that whatever you have today, whatever you say, is dependent on what you had yesterday, whether you use stationary processes or not. Stationarity doesn't imply independence between time periods, right? So this is a lot different context, and IID assumption about time series is irrelevant unless you have strict white noises.
Yeah, okay.
Yeah, so this is not about time series. This assumption cannot be put there. Something else could, but not this. So, okay. So we can still apply the results, this result, or the like we can change this result in the same manner like you did, for example, okay, homoscedasticity assumption is violated, then this matrix is not what we think it is, but we still can try to estimate it. And there's this huge trouble of estimating things under heteroscedasticity. If there's a violation of absence of autocorrelation, I think you called it like that, then still you can identify it, estimate the parameters, and make some corrections. So the same idea here, but more complicated corrections and more complicated tools are required, because now we don't have one of the major assumptions about the regressions. So we need to use a different set of probability theorems. First of all, we are going to go over them really fast because we don't have enough time. And then we will see what happens. So first, yeah, let's skip ergodicity. If there's time, we are going to discuss it next time. It is a theoretical property that cannot be checked from the data, but we needed to apply theorems about stationary and ergodic. You remember we also I talked about it a little bit in the beginning of the course when we started to deal with stationarity. I said that ergodicity is another property that we are going to need later. And luckily for us, in some sense, luckily for us, we cannot check it from the data, we cannot test it. This is something that we can only believe it. It has a huge technical definition that is very hard to understand, but for us, in our context of stationary or non-stationary even time series, ergodicity would mean that the dependence, if there is a dependence between the current value of some process and the same process shifted back in time, then as we shift further in time, so as this j goes higher and higher, the dependence somewhat decays. We don't know in which sense, but it's something like it diminishes, and it must disappear. So the infinitely distant that parts of the processes are, they become independent, but infinitely. Before they might be still dependent. This is the property of ergodicity. So of course, everything that is IAD is ergodic, but time series might be not ergodic. Non-stationary processes are not ergodic. Only stationary processes, or at least weakly stationary, must be ergodic. Can be ergodic. So we cannot test it, so we only believe in that. So and usually it is something really a plausible assumption about many economic time series or many economic processes. So the revenues of a firm, well, yeah, they depend on each other if they are ordered in time, but that dependence decays. Yeah, there might be even some seasonality and what happened, or some even cyclic component, and what happened this month depends on the same month last year. What happened this year depends on what happened maybe 5 years ago, because there's an economic cycle. But if we take this 100 years ago or 200 years ago, even if that thing existed, then yeah, of course it is not dependent, because a lot of things changed, and it's the same about other things. So this is just an assumption that we make about many economic things, and don't bother, because it's not testable from data in any way, because we don't observe infinite time series. Okay, so we are going to talk maybe about it in our empirical example tomorrow. And one of the examples I gave you, for example, revenues of firms or GDP, or GDP growth, if they are stationary, those are examples of ergodic time series, definitely. And then we have the first time series analog, not time series analog, but the extension to the time series case of a limiting theorem. So, which says this: so if we have xt, which is stationary and ergodic time series, that S and ETS, this is stationary and ergodic time series. Well, weakly stationary is enough. This is a huge luck for us. So strict stationarity is not required, because in the data we only can identify weakly stationary, so we can actually apply to things that this thing to what we get from the data. So if we have weakly stationary and ergodic time series X with such technical property, then yes, so not just the first moment exists, and not just the second moment exists, but this absolute first moment exists. It's finite, but for most weakly stationary time processes, it does. Then, as the size of the sample of the time series gets to infinity, we get this: the sample average, or the sample mean of that stationary and ergodic time series converges to its long run mean, right? So what is this theorem analog for? We just discussed it many times already, just used it many times, that name. This is the time series, stationary and ergodic time series case for something that we called what? In the case of random samples and IAD observations. some sample average converges to the population mean or population expectation. You saw it many times. Okay, this is the time series analog for the law of large numbers. Right? Luckily for us, it still works if this thing inside that we use in it to sample average, if this is a stationary and ergodic. Then again, in the OLS estimates for multivariate linear regression, we will get that this thing still converges to its sample analog to the expectation of this thing, which is the second moment of x. And then another limiting theorem is the so-called central limit theorem, but not the basic central limit theorem, but the central limit theorem for general dependent observations. This is another version of central limit theorem, which says that blah, blah, blah time series, not IAD series of variables, but blah, blah, blah something time series, not just with finite variance, but with finite something else. And then you get the same square root of the sample size, then average minus the expectation. This is what the classic theorem says, and it converges to the normal distribution with in distribution converges, of course, to a normal distribution with zero mean and some variance here. And this LRV stands for long rank variance. You see, it's not just variance because now just variance is the variance of this thing in one moment in time, but the long rank variance accounts also for dependency of that thing across time. It is not just the variance here in this huge infinite summation. The variance appears here when you get g equals 0, but then you also have the covariance of xt and xt minus 1 and so on. Basically, if you have IID here, instead of long-rank variance, you will get just variance plus a bunch of zeros, infinite bunch of zeros. And the theorem will be exactly the same. So this is just like one of many generalizations of central limit theorem. Not many, but one of them, and the one that we need. So this long-rank variance is something that exists for stationary time series. Unfortunately, it involves, again, infinite summation, and of course we don't know it for sure for the processes, especially when we don't observe the process directly in the data. For example, the error term, we don't know it, we can only estimate it, and it creates some trouble, but well, people came up with nice things to deal with it. The same way as you click that robust option in Stata, you can use options that will allow you to use these tools instead of, or will justify you using these tools instead of the usual IAD applicable tools. But we need to be able to estimate the long rank variance, of course. And the key idea is to learn to deal with this infinite summation. And basically, they are all based on the assumption that the process is not just stationary, but it is also ergodic. And when you get to infinity in JS, the dependence between those things should disappear, should vanish or decay. And since the dependence disappears, the covariance also disappears. And then it means that at some j, we can just cut it and don't consider j in absolute value larger than something, so some large enough value. Basically, the tail and that tails, both tails in plus infinity and minus infinity tails in that summation, they don't matter much for the value of long-rank variance. The most commonly used estimator for long-rank variances of stationary and ergodic time series is called New West estimator. And if you saw enough of that, if you watched enough of that online course on the macroeconomic forecasting, you saw that NW correction or NW hug estimator, or NW correction for standard errors, and so on. This is exactly it for the case of time series analysis in the regression context, instead of just robust standard errors or White's correction for standard errors, the one that we used in cross-sectional case of heteroskedasticity, right? People use New West correction that allows you to account not only for potential heteroskedasticity, but also for autocorrelation or autocovariance of the data, and it is necessary in time series. So this form is something. This estimator is something ugly, but basically, as you can see, J is not infinite here, but goes from some within some limits, and the limits depend on how much data you have. It depends on T. There is justification beyond this. There are many versions of this estimator that use maybe different M, different estimations for gamma, different weights here, but this is the most commonly used, and in the software, in case you see New West estimator or New West correction, this is what is going to be used by default. This formula shows you maybe two important insights. First, you have to have long data, and if your data is close to be non-stationary, for example, your data, the X, is close to be unit root, you know how this thing behaves, then it decays very slowly. It is like 0.9, 0.89, 0.88, and so on. And if you cut it at some point which is not too far from zero, that M, you're going to throw away a huge portion of that long-run variance, and the estimate basically is not going to be good. So it's better to have data that is coming from like genuinely stationary processes. And if not, then, well, some tricks need to be applied, maybe some transformations to the data and so on. This is the intuitive explanation, or like technically intuitive explanation of why data that are close to non-stationary are not good to be used as variables in regressions. And of course, non-stationary data at all give you no explanatory power whatsoever, because you cannot apply those theorems to them, and the estimates drawn based on the non-stationary data just from basic linear regressions, they mean literally nothing. So if you work with non-stationary data, there's all other sets of tools for estimated linear models, linear regressions, the so-called error correction models or covariance models, and unfortunately we have no chance to fit them in our short course. But in that online course, there is a block about non-stationary models also. So if you're interested, and this is very popular thing in macroeconomic time series modeling, but in other ways, the basic setup is about stationarity, of course. So this estimator also works for matrices, not only for scalar time series. So when you apply that to vector, for example, that's gamma becomes not just a number but a matrix. This looks even uglier, this form, but the basic idea is the same. Cut the infinite summation at some point M, which depends on how much data you have, and sum up weighted matrices there. And finally, in the last, well, I will have to delay you a little bit, I'm sorry, but not as much as the last time. And finally, we can reformulate the results that we have using these theorems and the additional assumption about our data that now is going to be drawn not from IID observations, not random samples, but from time series. Oh, the idea is the same. Now the index of observation is T, which means that these are time series and they come in specific order. You cannot reshuffle them because they are ordered in time. The regressors also come as some time series, but they can also, as I already said, they can also be lagged values. For example, yt can depend on previous values of itself. Here it might be a part of a regression. X's might be here themselves, so some explanatory variable or some control variable, and then also lagged versions of it. There might be only lagged versions. For example, yt can be GDP in the current year, and xt might be only some variables that are in the previous year. Well, not GDP growth, because we are talking about stationary data, of course. The notation is exactly the same. It's just that the index of the observation might mean something else. And the assumptions are different. So instead of random sampling assumptions, we now get time series assumptions, stationary time series sampling, that y-axis and epsilons are weakly stationary time series now, and the exogeneity of order is of error term is still here. So given the explanatory variables, the error has zero expectation, or the error term is uncorrelated with the regressors, with the controls. This assumption remains here. It means a little bit different thing now because it's time series, but still. And what is important here, we don't require the error term to be weak white noise. This is not realistic. This assumption sometimes done as the analog or time series analog of what we usually assume about the error term in cross-sectional regression, right? But we don't do that. First of all, because, well, our models are never true, and there are a lot of missing variables in whatever we are trying to explain. There's no way we are going to explain all by including some axes. We can try, but still it is quite reasonable to assume that this thing can be also auto-correlated with its previous values. So there might be some dependence between epsilon t minus 1, epsilon t minus 3, and so on. Because it's stationary and ergodic also by our some assumptions. Yeah, there, here it is. This dependence will decay and will vanish when you take further distant away from each other parts of time series. But still there might be some. Why this is important? Because, well, exactly because of that those theorems, because we will have to apply them, and we are going to need to use long-rank variance estimator for epsilon as well. The OLS works exactly the same. It gives you the same formula. The difference is also the same as before. It's that linear something multiplied by the error vector. And then by assumptions, it's still unbiased. By ergodic theorem and those assumptions, the difference still converges to zero as sample size converges to infinity in probability, though it is consistent. Same idea as before, just the theorems are different. And again, the theorem is different, but result looks exactly the same. So the this thing, the difference slowed down by the square root of t, converges to some normal random variable. But because in this difference there is this thing, and it is auto-correlated with each other, because epsilon is not white noise. Now it might be auto-correlated. X is just a stationary time series. It also might be correlated. When we estimate the this matrix, we have to use the long-rank variance estimator. And then the typical New West estimator of the variance covariance matrices of the coefficients looks like this. It is ugly as dark night, but this is what we get. And it shows you already the importance of using it, because if you don't, then you might miss a lot in the estimates of your standard errors and in the covariances of the coefficients between each other, and that means that the inference might change a lot. it is not necessary that it changes crucially, but generally when you work with time series, and if you assume that there might be some significant autocorrelation in your data and in your residual term, this is the way to apply. The same way as you sometimes automatically click in data, use robust, just in case. What if there's heteroskedasticity? If not, then not much will change. Okay, but if there is, we must account for it. Same idea here. New West heteroskedasticity and autocorrelation correction. This is what HAC stays for: heteroskedasticity and autocorrelation correction. In this case, it doesn't correct for heteroskedasticity much. It does like a little bit, but not as much. But also for autocovariance. In case there is heteroskedasticity, it will be automatically accounted for in the estimates of gamma. So it still will work. This is the time series analog for White's correction, the closest to it. Yeah, I'm closing part of it, but this last part here is the same as here, but so this is the so-called sandwich type of the estimate, where you have two different things on both sides, or two the same things on both sides, and then in the middle something that is like jammed together, like between two slices of bread. Yeah, again, luckily for us, in the software that estimates time series models, this thing is calculated automatically. You just need to choose the corresponding option. So I will not hold you any longer. There's the wrap up that in short says, okay, there is the whole set of tools that we can apply for random sampling, but for time series context, it is not applicable right away because, well, the theorems that we use to derive all the nice properties don't work for time series. But there are analogs of those theorems that work for stationary and ergodic time series. Hence, we can apply the multivariate linear regression almost without any change to stationary time series. Why stationary? Well, because then we will be able to apply those theorems. If the time series inside the linear regression are not stationary or not deterministic also work. For example, like those seasonality dynamics and stuff. If they are not stationary, then, well, sorry, your multivariate linear regression doesn't show anything, because all the inference that you are trying to do means nothing, because the theorems that are used to justify that inference don't work if the time series are not stationary. So the non-stationary time series models would be the next logical block of the course, but unfortunately this is the end point of our course. We are going to have just another wrapping up lecture, answering questions, filling in stuff, right, and discussing quizzes and so on. But this is the last theoretical point in our lecture. Tomorrow, in the practice session, we are going to consider empirical example and discuss an empirical example of a multivariate linear regression applied to stationary time series. I already announced that it's going to be some attempt to link GDP growth to housing starts, right? And we will see what difference makes applying the long-run variance estimator as opposed to just usual estimator that is used for IAD case. Okay, so that's it. Yeah, so this is the most important portion of this lecture. So new West heteroskedasticity and correlation correction, that new West HAC or NW HAC estimators is a must-have when you apply multivariate regression to stationary time series. That's it. If you have any questions, please stay and ask. If not, then see you tomorrow in the practice session.